Yeah, here we go. So melting layers in the atmosphere refer to the heights while falling ice particles melt into raindrops. And they characterize the vertical structure of phase transition in the precipitation system, particularly stratform rainfall. Melting layers are important for quantitative precipitation estimation and also for practical application in aviation risk management. The heights of melting layers vary with environmental conditions, including temperature, humidity profiles, as well as pressure and terrains. It generally ranges from several hundreds to a few thousand meters above the ground level. And accurate detection of melting layers carry profound implications for further understanding the precipitation development and its impact on the surface. For the detection of melting layers, there are currently the methods could be categorized into two main approaches. The first approach is dependent on environmental conditions and usually involve applying thresholds of air temperatures or wet bulb temperatures. So here the figure on the bottom showing the site observations of the temperature thresholds at which the rainfall and snowfall would occur at equal frequency in the northern hemisphere. We can see that actually this temperature threshold has a very distinct range and could be larger than 4 degrees Celsius, even in the Arctic region. So one caveat of using this approach, number one, is the melting process actually depends on multiple environmental variables, and using one uniform variable or one uniform threshold of particular variables could cause serious problem in the precipitation phase identification. And approach number two, on the other hand, provide a more detailed look at the hydrometeor characteristics. For example, if we are talking about radar observations here, then the radar reflectivity, Doppler velocity, and other radar variables such as the linear depolarization ratio would help us to better understand the size, volume, and optical depth or motion of the hydrometeor in the precipitation system. So the melting layers have been long observed and monitored by radar observations. This is because the melting process itself would exhibit distinct radar signatures. For example, the enhanced reflectivity due to partially melted snowflakes are more reflective, and accelerated Doppler velocity towards the surface, since raindrops generally fall faster than the snowflakes. There have been various detection algorithms developed for ground-based cloud and precipitation radar, and these studies have provided complementary insights to satellite measurements, especially in the cases where the melting layer heights fall within the satellite radar blind zone. However, traditional detection algorithms are usually based on empirical assumptions or fixed thresholds, and therefore they usually lack general applicability in different weather conditions. For example, here I show two radar observations of Doppler velocity in different rainfall intensity cases. For the left side case, where we see this distinct separation for Doppler velocity of raindrops and snowflakes, it's perfectly fine to apply a Doppler velocity larger than 3 meters per second thresholds for phase identification. Meanwhile, for the right side case, where we see this deep bluish color referred to the velocity folding, this occurs when raindrops fall faster even faster than the maximum measurable range of the radar instrument. So in this case, the heavy rainfall, stratform rainfall case could cause a problem when it comes to using the same criteria for phase identification. Therefore, in addition to the velocity folding case, the traditional detection algorithm would also struggle to detect melting layers in other complex weather conditions as well, including multiple melting layer cases and discontinuous rainfall, and also the melting layer are very close to the surface. So this leads us to the scientific question of giving the same radar input, can we do better with the melting layer detection? And in this study, we're looking forward to use machine learning technique and help us under this question. So to train a machine learning model well, first thing to do is to prepare your input and output data set properly. And in this study, the input data set comes from Ka-band Zenith radar, also known as KAZR, installed at the North Slope of Alaska. The KAZR observations from March 2015 to February 2016, including radar reflectivity and Doppler velocity, have been collected from this site under various weather conditions. So for the output melting layer masks, we have no available dataset for use. Therefore, we developed this data extraction tool named ClickClack to help us generate melting layer masks from radar observations. ClickClack provides an interactive platform for the users to put their cursor on the figure and then click on the melting layers as shown by this deep bluish color in the Doppler velocity gradients. And one great thing about ClickClack is it provides this flexibility for you to refining your selection of data points, so you do not need to worry about mistakes during the click process. And after we're done with the upper boundary, we can also do the same thing with the lower boundary. Please also note that this tool knows nothing about radar or meteorology, so it can also be adapted for wider applications. And we have provided the codes available for use in our GitHub repository. So now we're done with the lower boundary of the melting layer as well. We can have another chance to get a review of what we selected just now, so that you can make sure, okay, the melting layer looks correct. And in this way, we have collected our output melting layer masks to train our machine learning model. So let's keep moving on to the data pre-processing steps. The radar observations have been segmented into smaller data chunks, each of them containing 16 minutes of radar observations. And in total, we have collected over 700 hours of reflectivity, Doppler velocity, as well as its vertical gradient. These data chunks are then normalized and combined with the corresponding output melting layer mask of ClickClack to go through the data splitting step into training, validation, and testing datasets. We want to emphasize that the data segmentation and the non-shuffle splitting strategy adopted in our study has helped to avoid data leakage due to the potential temporal autocorrelation in our training dataset. And for the machine learning part, we used a UNet model. It's a specific convolutional neural network with U-shaped architecture, and it has been designed for image segmentation. The UNet model is also known for perform accurately and efficiently with relatively small size of training dataset. We have also conducted hyperparameter tuning to further improve the performance of this UNet model. So what happens in the training is the radar observations will be normalized and fed as input to the UNet model. This dataset then goes through the downward passing way composed of these encoder layers, which will focus on compress the radar images by reducing its spectral size, meanwhile increasing its dense, so that the UNet model will be able to extract the feature maps from the observations. These feature maps could be highlighting the difference of the precipitation system against the background noise, or it could be focused on the difference between the rain echoes and the cloud echoes. So after it reaching the deepest layer, it will then go upstairs and go through this decoder layers, which will gradually reconstruct the spatial dimension of radar images to give this output melting layer probability for each pixel in the input dataset. So here we pull out the activation output filters for the first encoder layer in the trained UNet model, so that we can like have a direct look at the model, what it's trying to learn from the radar observations. And for example, for certain filters like filter number 2 and filter 38 here, this filter is trying to highlighting the overall precipitation system out of the background noises. And there are also some other filters like number 8 or number 40 or 55. They're trying to focus on the melting layer itself. So the interpretations of these feature maps could vary with specific case. However, by showing this filters activation, these feature maps, we're trying to emphasize that the UNet model is capable to learn from the spatial information of precipitation system and clouds and rain and melting layers from the original radar observations. In this study, we have also implemented a traditional algorithm to compare against our UNet model. This traditional algorithm is a 3-step decision tree, and it's based on empirical thresholds of radar observations. First, start with precipitation occurrence identified by this radar reflectivity threshold. And then we want to know that there is rainfall. So we use Doppler velocity to do the phase identification. And the last step is melting layer identified by this Doppler velocity vertical gradient thresholds, first applied by White et al. So the detection performance in this study is evaluated from 2 levels. First is scene-wise accuracy. This is to evaluate melting layer occurrence in this case, basically to see whether melting layer exists or not. And the other one is the pixel-wise accuracy. This is to evaluate the melting layer location and shapes and look into the pixel-wise characteristics. So the results of melting layer detection on the testing dataset have shown that the UNet model effectively identifies majority of the melting layer occurrences and also greatly increase the amount of successfully detected melting layers from 70 here to 110. That's by like 57%. And here, the detection performance diagram shows the success ratio on the X and the probability of detection on the Y-axis. The contour lines refer to the critical success index. So in general, we want to see a detection results line in the upper right corner here. And so for both the traditional and the UNet model, we can see that they have high success ratio. This is good because it means they both have little false alarms. Meanwhile, the UNet model has increased the probability of detection and also the critical success index by 50% compared to the linear method. This means that the UNet model is able to pick up more melting layer cases that would have been missed by the traditional one. And we have also shown this dashed line here. This refers to the frequency bias, while those below the 1-to-1 line indicate that model is trying to underpredict melting layers, which is exactly the case for the traditional algorithm. So this means that the traditional algorithm could be a safe but too conservative algorithm when it comes to melting layer detection. And on the other hand, the UNet model is more closer to the 1-to-1 line. It indicates that the UNet model has addressed the underprediction bias well compared to the traditional algorithm. So now we're looking into some pixel-wise accuracy of the melting layer detection. Here we have two evaluation matrix, dice coefficient and the intersection over union. This two evaluation matrix measures the overlap between two geometric objects. So compared to traditional algorithm, the unit model has increased the both of the evaluation matrix, and this indicates there is an enhanced similarity between the melting layer detection and the ground truth. From this, we can conclude that the unit model is also remarkably proficient at characterizing melting layer location and shape. So now let's look into some very specific cases so that we can have a better understanding of how well does the unit model works with different weather conditions. So for example, here we have the Kaiser observations of radar reflectivity, Doppler velocity, and also the vertical gradient of Doppler velocity showing on the right, on the left side. And starting from the traditional detection results, which is nothing detected, and also the unit model of composed of ensemble mean and its uncertainty. So one interesting thing that you probably have noticed is we have detected this concurrent melting layers here. And this could be due to multiple freezing levels in the atmosphere or different groups of ice particles in the precipitation system. And so we think it's very interesting that the unit model have detected this real phenomenon, and it's meaningful for further investigation. And similarly here is another case, but this time in July, and it's a very heavy stratiform rainfall case. We have the case observations here. You can see again, we have saw these folded radar signals indicating that the rainfall intensity is strong. And for such case, the traditional algorithm would have a difficult time trying to identify the melting layers from these folded radar signals, as well as some echoes on the top of the cloud edges. Meanwhile, the unit model has been well trained with these cases and perform much better compared to the traditional one in the melting layer detection, and also provides this uncertainty of melting layer detection here. So last, we want to show a very shallow melting layer case located below 500 meters above the ground level. This is interesting because for the traditional algorithm, this shallow melting layer cases are usually associated with relatively weak radar signals. So it can be hard for the traditional algorithm to get them correct. Meanwhile, the unit model is able to pick the whole melting layer up, and therefore would help us to have a better understanding of such shallow melting layer cases. And so brief takeaways, we have developed a unit model style or based machine learning technique to help us improve the current detection of melting layers. And this unit model has increased the detection accuracy of melting layer, not only the occurrence, but also the boundary heights and also the shape. The unit model performed robustly across diverse weather conditions, which is a great improve compared to the traditional one. The unit model works well with heavy stratiform rainfall with folded radar signals, and works well for shallow melting layer cases, as well as concurrent melting layers. In addition, we have also implemented ensemble predictions of the unit model so that it can provide us with a quantitative estimate of model uncertainty. This is very important for us to understand the reliability of such a machine learning technique. Last but not least, the methodology presented in this study are applicable to similar instruments over wider regions, and will help us to have a better understanding of the development of precipitation, as well as its impact in the future climate. The codes are all available from this GitHub repository, and I'm happy to share that the paper on this work just got accepted like yesterday. So with that, I will conclude my presentation, and thank you very much for your attention.
So we will now head over to our next speaker. In the meantime, please feel free to uh, ask your question in the chat box. Thank you so much, Ian. That was a great presentation. So
Thank you.
our second speaker for today is Ann Sinclair. Let me give a brief introduction of Ann. So Ann is a second-year PhD student in the Department of Earth, Environmental and Planetary Sciences at Northwestern University. Her research centers on characterizing uncertainties in precipitation over areas of complex terrain and understanding how these uncertainties affect landslide assessments and hazard early warning systems. In addition to her uncertainty analysis work, she is also using deep numerical simulations to study the behavior of moist convective thermals in the atmosphere. Before starting her PhD, Anne earned her bachelor's degree from Swarthmore College, where she majored in astronomy and environmental studies with a focus in environmental philosophy. So take it away, Anne, and everyone enjoy the presentation.
Okay, thank you so much for that introduction, and thanks again for having me. I'm really excited to share my research with all of you. So I'll go ahead and share my screen, and we can get started. Okay, so the title of my presentation today is Uncertainty Among Hourly Precipitation Estimates for Shallow Landslide and Debris Flow Events in Southern California. And I wanted to start off with some motivation and context for sort of why I started working on this project. I came to grad school in August of 2023, which was right after post-tropical storm Hilary hit Southern California. And our group had some collaborators in the landslide world who were wanting to study the mudslides and debris flows that occurred as a cause of this storm. And they had asked our group to look into which precipitation data sets they should use to look at these land surface hazards. And so I started to kind of look into that question, and what I realized is that the answer isn't really that simple, because there are some data sets that maybe do better in some contexts and some data sets that do better in the other. But I was really interested in this question of like, well, what does it mean for landslide research and landslide researchers that different precipitation data tell different stories about the same event? And I think to understand why this is an important question, or why this is something that, you know, landslide researchers might care about, it's important to have some context for why precipitation data is important for landslide research in the first place. And the reason is because rain acts as a triggering mechanism for a lot of land surface hazards. I want to say in this project, I've been focusing only on shallow landslides and debris flows. And so there are also deep-seated landslides, and precipitation data is also implicated in the triggering mechanisms for those things, but I am not thinking about those for this project, so I'll only be talking about shallow landslides and debris flows. But I'll just briefly go over how precipitation is important for the triggering of those events. You can have infiltration triggered landslides. And so in this context, you have rainfall, and it comes down and kind of increases the soil moisture of a slope, increases the pore water pressure, and that can lead to a decreased slope stability. And so then eventually, if you have a trigger, and that can come in the form of like another precipitation event, then you can have slope failure and a landslide that occurs. The other way that rain can act as a triggering mechanism for shallow landslides or debris flows is through runoff. And so if you have rain that's coming down, causing runoff over a slope, then it can pick up sediment or material and result in a mudslide or a debris flow. And so in both of these contexts, landslide researchers need to know about the rain sort of on an hourly or sub-hourly scale in order to understand how that rain triggered a land surface hazard. Which means landslide researchers need precipitation data, and they use that precipitation data in a lot of different applications. These include things like post-hazard assessments, so trying to understand or characterize an event after it's occurred. Precipitation data is a really important input into hydrological modeling studies. And it's also used to develop early warning systems that are used to try to predict when and where landslides might occur and keep communities safer. And so, as an example of that, this is a figure I just pulled from a paper by Dennis Staley et al. From 2013, but it's showing precipitation data plotted with intensity on the y-axis and duration on the x-axis. And this is an example of how precipitation data in conjunction with, when and where debris flows happen can be used to try to determine a threshold. And those thresholds are then used as inputs to early warning systems. So like forecasters might use this kind of information to decide when they're going to send out a warning to a community or like when it's time to evacuate a community. Historically, landslide research, this kind of study, has been done with gauge data. But as I'm sure everybody here is aware, there's now a lot of different gridded precipitation products that are also available, and there's been sort of movement in the landslide community towards using some of those gridded products. But in order to do that, it's important that we understand how those products are performing in the context of landslide triggering precipitation. And I think there's been, a fair amount of work that's been done trying to look at the differences among different gridded quantitative precipitation estimates. But landslide applications in particular pose some unique challenges. And so one of those is the fact that famously landslides tend to happen in areas of complex topography. And so you have rainfall that's varying really quickly over short distances. And the other thing is that in the landslide world, we tend to care about precipitation on really small spatial and temporal scales. Right. And so like a landslide researcher might be concerned with the precipitation, the kind of hourly or sub-hourly intensities that occurred in the hour or two before debris flow happened over the catchment where that debris flow occurred, rather than, a daily or annual accumulation over a larger area like the US or the Western US. And so all of this has, I guess, motivated me to look into this research question, which is, what is the hourly uncertainty among gridded quantitative precipitation estimates during landslide triggering events in Southern California? And in this project, I've been focusing specifically on Southern California, and that's for a few reasons. This is a good area to test this question because there's a wide range of available gridded QPE products. And there's also relatively high gauge density, which means we have some context for ground validation. And then finally, this is an area where that's vulnerable to shallow landslides and debris flows. And so there's a lot of landslide research happening in this region. So I'll briefly talk about my data and methods for this project. I compared quantitative precipitation estimates for 6 storms that happened from January 2021 to August of 2023. I chose these because they all happened after all of my precip data was available, and they all caused multiple documented landslides and debris flows in the study area. And so across these 6 storms, I compared precipitation at the times and locations of over 100 shallow landslide and debris flow events. Getting into my precipitation data, this is like the meat of it. I compared 13 different QPEs for these landslide events, or I guess gridded QPEs. And these were chosen based on the fact that they were publicly available over Southern California, and that they all had temporal resolutions of an hour or sub-hourly. So I'm not going to talk in depth about all of them because we'd be here forever, but I'll just like briefly go through the kind of major categories. So I looked at 2 radar-based products, the MRMS products, as well as 2 gauge blended gridded products, and those were NCEP stage 4 and NLDAS2. I looked at 5 different satellite-based products, and 3 of those were blended passive microwave and infrared instruments, and then 2 of them come just from infrared observations. Then I looked at 3 reanalysis products. And finally, I also used the output from the high resolution rapid refresh model. And I looked at the forecast hour 1 and forecast hour 6 estimates from that model. And to compare against all of these gridded products, I also compiled a fairly extensive set of gauge data over the study area. This is showing the locations of all of the gauges. And so they came from a few different sources, but altogether I had about 2,000. And I did kind of put them all through the same quality control process before I used them to compare to the gridded QPEs. Okay, and so I guess like my workflow for this project was pretty simple. Collecting the data was definitely the most time-consuming part. And then I compared the 13 gridded QPE products as well as gauge data at the times and locations of the landslides that I was looking at. And finally, I analyzed the results. Okay, so speaking of results, we can get into it. The way I want to do this is I want to walk through a couple of case studies first and kind of show what the precipitation was at specific landslide events. And we can like put on our geomorphology hats and pretend that we're landslide researchers and like what would it mean to try to pick a precipitation product for these events. And then I'll go through some more general trends that we see across the board. The first case study that I want to walk through occurred as a result of post-tropical storm Hillary. And this debris flow was in Forest Falls in San Bernardino County. So I have a little video of it. So you can see all of this like material coming down the slope, and then it actually comes down and like blocks this roadway. And so I guess the question is, what is the precipitation that caused this event to happen? So this plot is showing the recorded precipitation from the nearest gauge. This gauge is about half a kilometer away from the site of the debris flow triggering. And so that's plotted in black, and then the gray band is showing the spread among all of the different gridded QPEs that I looked at, and so that'll just be for context as we go through. So if we take a look at our radar and gauge blended products, we can see that those are matching pretty well in terms of timing with the gauge, but they're capturing lower intensities in this case. The satellite products are also capturing lower intensities than the gauge did, but they're peaking several hours earlier. Our reanalysis products are showing pretty significantly lower intensities, and that's not particularly surprising because reanalysis products they have coarser resolutions than the radar and satellite-based products that I was looking at, and so it kind of makes sense that the intensities are lower. And then our forecast model output is actually, in this case, matching pretty well, both in terms of timing and intensity with the closest gauge. Altogether, this is what everything looks like on top of each other. I have a friend who calls this my spaghetti plot, because it's just like a lot of stuff all together on top of each other. But I put it up here to show how many different stories are being told for the single time and single location. The second case study that I want to walk through happened in January 2023 as a result of an atmospheric river, and this one was in Fillmore in Ventura County, California. So here's a picture of the aftermath of this debris flow, and it ended up damaging an avocado farm and then depositing sediment and debris onto State Route 23. And so again, we have a time series showing what the closest gauge recorded. In this case, this gauge is about 3 kilometers away from the site of the debris flow. And again, the gray band, it's going to be the range among the different gridded QPE data sets. So as opposed to the last case study, in this case, the radar and gauge blended products are actually capturing somewhat higher intensities than the gauge does. And the same thing goes for the the satellite products, in this case, we have at certain times they're capturing slightly higher intensities than the gauge. And you can see that also they're more aligned in terms of timing with the gauge than in the Hillary case study. Again, our reanalysis products are maybe slightly lower intensities, and the same thing goes for the forecast model products. And so once again, all together, here's everything on top of each other. And, I'll say it again, many different stories are being told about this same precipitation event. But the reason why I think it's important to show both of these case studies is that the product that you might choose with the information that you have for this landslide would probably be different from the product that you would choose with the information that you have for the Hillary landslide. And you can imagine that if you're a landslide researcher, and especially if you're trying to study an event that occurred where you don't have gauge data to kind of compare against, that it might be really difficult to choose among these different products and to know which one to use for your study. The last thing that I want to say in the context of these case studies is that for both of the ones that I just walked through, there were products that matched relatively well with the gauge data and, maybe with some of the other products. And I just want to say that that's not always the case. And so there are some times where like everything is just kind of going crazy. And so I just want to show one example of that. This is a time series from a January 2021 atmospheric river, and I'm just putting it up here to show that like it's very hard to tell what's going on here in terms of timing and intensity of precipitation, and a lot of the different products are telling very different stories. So we can also look at some overall trends across the 100 or so landslides that I analyzed. These plots are showing hourly intensities at the landslide locations. And so on the x-axis, we have the hourly intensities that were captured by the closest gauges. And then on the y-axis, we have the hourly intensities from our gridded QPE products. And this is helpful to get a sense of patterns of over versus underestimation for the different products compared to the closest gauges. And so just kind of like a couple of things that I can point out. We can see that in general, most products tend to overestimate gauge data at lower intensities and underestimate them at high intensities. This pattern is especially true for the satellite and reanalysis products, where it seems, maybe with the exception of CMORPH, that there's kind of like a cutoff intensity around like maybe 15 millimeters an hour, where they don't tend to capture intensities much higher than that. The same thing isn't so true of the radar, gauge blended, and forecast model products, but in these cases, we have, some more significant cases of overestimation. The other kind of overall trend or pattern that I want to talk about is this idea of spread. And so this plot here is showing on the x-axis, it's the highest reported intensity at a given hour at the landslide locations that I looked at. And so that's like among all of the 13 different gridded QPEs that I looked at, which one is reporting the highest intensity, and then what is that intensity for a given hour. And then on the y-axis, it's the spread or range of reported intensities among the different QPEs for that same hour. And so we can think of the x-axis as being kind of like a maximum, and then the y-axis as being like a max minus min for a certain hour at, a landslide location. And basically this plot just looks like a straight line, like a one-to-one line, which tells us basically that the spread among QPEs at these landslide locations is pretty much the same as the highest intensity reported. Or another way to say this is that whatever the highest intensity is that's recorded at a given time and location, you can always find another gridded QPE product that tells you there was little to no rainfall at that same time and at that same location. And what that means, for landslide researchers is that there's not really a good way to get a lower constraint on the triggering precipitation for a landslide event. Okay, so I'll just go through or wrap up with some conclusions. I hope I've hammered into everybody's brain by now. You're probably sick and tired of hearing me say it, that there are really substantial differences among graded quantitative precipitation estimates during landslide triggering events, especially at these hourly temporal scales. Um, and that there's no single product that performs, the best in terms of matching with gauge data for every single landslide or every single hour, every single storm. So there's not really like one best QPE product, and there's a lot of uncertainty among them. And so for landslide researchers, what this means is basically that it's hard to choose. But I guess to be more specific, and what I tend to try to say when people ask me, like, well, which precipitation data should I use? That I think it's important to look at multiple different products in order to get a full sense of what the triggering precipitation might have been. And also that it's important to basically take that uncertainty into account when doing landslide research. And so one of my next steps is working on code to try to make it easier for landslide researchers to actually compare different graded QPE data sets at the times and locations of the events they want to study. And then for folks who work more in the QPE world, what I would say is that landslide research is not the only application where these kind of short temporal scale precipitation estimates are important. And so validation of precipitation estimates at these hourly or sub-hourly scales could be really helpful and really crucial for applications like land surface hazard research that rely on, the hourly and sub-hourly precipitation information. Okay, thank you all again for having me here, and I'm excited to, answer any questions or just have a little discussion.
Amazing. Thank you, Ann. Thanks to both of our speakers. Those were excellent talks. And it's great to see actually some of the connections, thinking about precipitation aloft and as well as how that impacts surface processes. So that was great. So what I think we'll do now, as we still have a few minutes left, is we'll take some questions in the chat as well as just live questions. So if you're thinking of something now while somebody's answering a question, feel free to post that in the chat and we can go through it. Or we'll maybe take a break in between chat questions and just ask for live questions as well. So feel free to do either. And so maybe I'll start with one for Jan, posted by D. Meyer in the chat here earlier. It says, excellent presentation. This model was trained on vertically pointing radar data. Radial velocity in that case measures something close to the true vertical velocity of rain as it falls straight down. Operational radars measure radial velocity with the antenna tilted at different angles. And so they do not measure the vertical velocity directly. How could your methods be extended to tilted radar data?
Yeah, thanks for the great question. So I guess the method provides a general framework. So if you have tilted, like observations from tilted radars, you could adopt the same framework and then apply your own data to train your own model. And meanwhile, the other approach I would think was wise trying is the transfer learning. So it's machine learning model. So you could apply the trained model of my work as the base for your tilted radar case, and then trained the vertical version with the tilted radar observations, and then it will provide increased accuracy as expected, or it will require less training data set. So with that being said, another thing I want to mention is what the model is trying to pick, or what we hope it's trying to pick, is the difference in the hydrometeor, or the change of the hydrometeor properties. So that should not be as dependent on like viewing perspective or viewing angles. And it will be interesting to see some of the cases, and I would say it's worth trying. So I guess I hope that I answered the question. Or should I continue to the following question? Or transfer it to, okay, thank you.
I might ask a question for Anne, so we can just go back to Yan again. So thank you so much for both of you. Thank you so much for the presentation. So I have a quick question for Anne. Like, are you planning to, merge different QPs and see how it, behaves in terms of your landslide analysis in future?
Yeah, thank you. That's a good question. So I'm not sure that I don't know that I would necessarily merge the different QPEs, especially just because they're kind of fundamentally like measuring different things. But I think there's benefit to thinking about like looking at the precipitation measured by many different QPEs because some of them are able to capture higher intensities than others in certain contexts. And so I think less about merging them together and more about finding ways to make it easy for people to look at all of the different ones that are out there and sort of get a better sense of what the differences are and what the different stories that are being told are.
Excellent. Okay, maybe we'll swap back to Jan again. Another comment in the chat here. Thanks, Jan, for the great presentation. What type of normalization technique did you use in the data preprocessing step? And what do you think this would, and do you think this would work for vertically pointing micro rain radar instruments as well?
Wonderful question. So to the first one, for the Kaiser observations, the noises and background like echoes in the Kaiser observations is masked and treated as clear sky conditions, which means for radar reflectivity, we set it to negative 60 dBz. And for the depth of velocity, we set it to 0 meter per second. So basically, we want to say that there's nothing there except the actual precipitation system itself. And this processed data set are then normalized to -1 to 1, like this range. And then so we have a consistent scale to train our UNet model. So the second question is, yeah, absolutely yes. We expect this to work as well on the vertical point, the MRR. And actually, we are planning on doing that in our next step research so that we can extend not only Kaiser, but also include the MRR measurements at North Slope of Alaska that will in total give us nearly 30 years of radar observations to study the precipitation and especially the stratiform rainfall in that site. Yes, thank you.
Thanks, Jan. I had a follow-up for Ann, actually. I was wondering if you could talk a little bit about your calibration process used for the in-situ gauge network. It's so vast down there, it was just great. I'm always jealous when you have such a wealth of information to work from. But with so many different networks and gauge types, I'm wondering sort of what work went into standardizing and calibrating that for your research.
Yeah, thank you. A lot of work, actually. And it was because there are so many different networks out there and so many different just instruments collecting, it was a lot of by hand work. So like writing algorithms to pick out things that like were like flagging different, if there was like a really, really high spike or like negative precipitation data recorded because that can happen sometimes and like going and either cleaning those or eliminating those gauges. And then I used Atlas 14 as well to get a sense of what the kind of normal or like expected precipitation could be even on the like really extreme ends. And so trying to eliminate maybe unphysical quantities that were recorded when you have gauges that are malfunctioning. So yeah, it was kind of a combination of like writing algorithms and then also going in by hand and like trying to pick out problem children that were there.
That's great. Yeah. I always talk about this sort of 80-20 rule with these types of projects where, almost 80% of the time is really spent on data collection and cleaning, and all the fun stuff of working with it is like the 20% at the end. So, okay, we'll do maybe one more for Jan. Great talk and congrats on the paper being accepted. I have a question regarding the click collect method. Does that mean all the cases would be manually cleaned and the melting layer would be manually identified first? And will this process, or will this be a reason for better performance?
Okay, so I guess I just talk about how this click collect is being used to collect or like generate the data set we're used to train the model. So in this study, we have include melting layers cases, but also other cases such as clear sky cases and cloudy sky cases, and also precipitation cases of snowfall and drizzle. So it's not only stratiform rainfall or only rainfall cases with melting layer. And we're trying to include this different weather conditions because we hope to apply this unit model and the click-clack tool in the future to a general data set instead of like a data set of containing melting layers cases only. And hopefully that answered the first question. And also I want to add that there is a substantial portion in the data pre-processing steps of manual label, which means me sitting in front of the computer and clicking all the melting layer masks. So with that being said, that is a certain part of uncertainty in our detection results or accuracy that is can be attributed to like human eyes viewing those pixels in a computer screen. So and we're also looking for a better way to constrain that uncertainty, but that's just at the initial phase. And will this be a reason for better performance? I'm not sure. This question is asking how the click-clack like manually collecting process would impact the detection accuracy. If that, I would say it's more uncertainty instead of like for sure increase or like for sure decrease. So yeah, the answer to the second question is I don't know yet. Hopefully it's not substantial. Yeah.
We have another
Thanks.
question for Anne. Thanks, Ian. Sorry. We have another question for Anne from JJ Gurley. So basically a comment and also a question. So your results agree with several other studies that have conducted intercomparison in various parts of the US and the world. Regarding MRMS, did you get a chance to examine the radar quality index product to determine if the region was well sampled or not? Another question is, did the WX underground gauges get any QC applied? Gauge quality can be better or worse than radars sometimes.
Yeah, thank you for this question. So in terms of the MRMS radar quality index, I haven't looked at that in comparison with like then how the MRMS products do compared to gauge data, but I think that would be really interesting to examine. So that's definitely something that I want to take a look at in the future. And I was also recently talking to somebody in my group about doing a little analysis about how well these products are doing compared to then like how far gauges are. So I think that there's like interesting analysis that can be done here. And then regarding the weather underground gauges, they definitely did get quality control applied. And just, I guess, sort of overall regarding this, something that, because gauge quality, as you say, can be, poor. And so gauges are like what we have for ground validation, but I think that there are contexts and times where I don't necessarily believe the gauge or there I might believe, a gridded product more than the gauge. And so it's like it's what we have, but they're certainly an imperfect comparison tool.
Great. Well, just keeping my eye on the time here, we should probably close out, but I want to send one more round of applause for both of the speakers here today. Thank you for joining us and for presenting your work, as well as the excellent discussion after. I'm sure if people have further questions, they can reach out to either of you, I would guess. Through email to answer those. But again, thanks everybody for joining today. Thank you to the speakers, and keep your eyes peeled for upcoming sessions, as we still have additional award winners that we'll be presenting in a few months' time at the next ECSPrecip award session. So thank you, everybody.
Thank you. Have a good one.
Thank you.
Thanks so much.
Bye.